name is Aragoneses, and I'm going to be your physics professor. In the following weeks, we will enter and explore the world of physics, and we will study diverse fundamental aspects that constitute the basics of physics. Physics aims to describe the universe from the tiniest subatomic particles to the origin and evolution of the universe as a whole. To describe nature, physics is supported by quantitative measurements. These measurements are obtained from experiments and observations, and are compared to models and theoretical predictions. To describe the motion of objects, we need to make measurements of distances and time intervals. All measurements are indicated with proper units and the errors involved in the experiment. The units we use in science are the SI system of units, where we measure distance in meters, mass in kilograms, and time in seconds. We use some standard references for meter, kilogram, and second, to which we refer when we give a quantitative result. In case we need to convert magnitudes from one unit to another, we will use conversion factors, which only consist in multiplying by 1 in a clever way. If we want to convert 60 miles per hour to meters per second, we convert from miles to meters and then from hours to seconds. We multiply by the relation between miles and meters and by the relation between hours and seconds. Then we find that 60 miles per hour is 28.81 meters per second. Let's get into kinematics. Let's talk about displacement and average velocity. In kinematics, we base our calculations in measurements of positions, displacement, time intervals, velocities, and accelerations. Let's consider motion in 1D, motion in a straight line. We need to choose an origin of positions, to which refer all the measurements of position, and an origin of time, to which refer all the measurements in time. We define the average velocity of an object as the displacement or change in position of an object that occurs in a specific time interval. Imagine that Superman is moving along a straight path with marked posts every 100 meters, and we observe that he passes one of the posts every 4 seconds. The average velocity of Superman during a specific time interval is the displacement divided by the time elapsed. The average velocity is proportional to the displacement, and it has the same direction. In this case, because Superman travels the same distance every 4 seconds, he is traveling at a constant velocity. If we plot the distance versus the time elapsed, we obtain a straight line, and the slope of the line is the velocity. The faster Superman travels, the larger the distance he makes in the same amount of time, then the faster he goes, the larger the slope of the straight line. In this case, the average velocity is the same no matter what time interval is chosen to calculate it. In this case, we say that the motion is uniform. Motion that is not uniform is said to be accelerated. In those cases, the average velocity does depend on the time interval chosen to determine it, as the velocity is changing in time. We will designate the straight line along which Superman is moving as the x-axis. We choose the origin of the axis to be at the first post. We also choose time to be 0 when we start measuring, when Superman passes by the first post. Following this, when time is 4 seconds, Superman's position is 100 meters. When it is 8 seconds, Superman's position is 200 meters, and so on. With this, we can define algebraically the average velocity as delta x divided by delta t, where the Greek letter delta refers to the difference in position x and difference in time t. This definition of average velocity holds whether velocity is constant or not. When an object follows a uniform motion, its position to time graph is a straight line. If the motion is accelerated, the graph is not a straight line, and the average velocity depends on time. We can describe the motion with the following equation of motion. X of t is equal to x naught plus v t minus t naught. Let's now study a motion that is not uniform. Consider that Supergirl starts at rest and travels increasing her velocity at a constant rate. Let's say that the first second she travels 10 meters, the second she travels 20 meters, the third second she travels 30 meters, the fourth second she travels 40 meters. Her motion is not uniform. Therefore, her position-time graph will not be a straight line, but a curved one. In this case, because she increases velocity at a constant rate, she describes a uniformly accelerated motion. She has a constant acceleration. This motion is described by the equation x of t is equal to x naught plus v naught t minus t naught plus 1/2 of a t minus t naught squared, where v naught is the velocity at zero time and a is the constant acceleration. This equation of motion describes a parabola. Instantaneous velocity. Most situations of interest involve accelerated rather than uniform motion. Since the average velocity depends on the time interval, if the motion is accelerated, it is often useful to characterize the motion by the instantaneous velocity, which is the velocity at a particular instant in time. In the case of Superman, his average velocity is the same as his instantaneous velocity. In the case of Supergirl, they do not coincide. To define mathematically the instantaneous velocity, we can calculate the ratio of delta x and delta t by making the delta intervals infinitesimally small. So the velocity is the limit when delta t tends to 0 for delta x over delta t, which is the same as the derivative of position with respect to time. In a graph, the derivative at a point is the slope, the tangent of the curve at that point. If the motion of an object was more elaborate than the one of Supergirl, if we had the algebraic expression for the position in terms of time, we can apply the rules of differentiation to find the instantaneous velocity of the object. From now on, when we talk about velocity, we will be referring to the instantaneous velocity, unless stated different. We will mention average explicitly when it applies. Also, velocity has magnitude and sign, positive or negative, depending on the direction of the motion. We differentiate velocity from speed, as speed is only the magnitude. Let's talk about acceleration. Like the position, the velocity can change with time. The rate at which the velocity changes is the acceleration. We can talk of average acceleration and instantaneous acceleration. The average acceleration from time t1 to time t2, if velocity changes from v1 to v2, is defined by the change in velocity divided by the change in time. If we measure the position in meters and the time in seconds, the velocity is measured in meters per second and the acceleration is measured in meters per second squared. If an acceleration is of 3 meters per second squared, this means that the velocity increases by 3 meters per second every second. The instantaneous acceleration is defined as the limit of the ratio between delta v and delta t. Just as with the definition of instantaneous velocity, the instantaneous acceleration is the derivative of the velocity with respect to time, or the second derivative of the position with respect to time. Remember that because the derivative of a graph is its slope, if we plot velocity versus time, the slope is the acceleration.